Hello, welcome back. In this lecture, we will learn joint probability distribution of a pair of continuous random variables. Many problems in probability and statistics involve several random variables simultaneously. Here we consider two continuous type random variables and their joint probability density function. We know that the probability that the observed value of a continuous random variable x lies in a one-dimensional set A, for example, an interval, is obtained by integrating the probability density function fx over the set A. We can extend this concept for two random variables at a time. Similarly, the probability that the pair xy of continuous random variables falls in a two-dimensional set A, such as a rectangle, is obtained by integrating a function called the joint density function. Definition of joint probability density function. Let x and y be continuous random variables. A joint probability density function f of x comma y for these two random variables is a function satisfying f of xy greater than or equal to 0 and integral minus infinity to infinity, integral minus infinity infinity f of xy dx dy is equal to 1. Then for any two-dimensional set A, probability that the pair xy belongs to that two-dimensional set A is equal to double integral over the region A f of x comma y dx dy. See, all these concepts are similar to single random variable continuous case where a function f of xy is said to be a density function of the continuous random variable provided it must satisfy the non-negativity condition and the total integral from minus infinity to infinity, that density function is equal to 1. Here also the two-dimensional function f of xy must satisfy the condition of non-negativity and the total area under the surface z is equal to f of x comma y above the xy plane must be equal to 1. And if you are considering a part of the xy plane, say set A, then the probability that the pair of continuous random variables belongs to that subset A is equal to double integral over the region of f of xy dx dy. Consider an example of two-dimensional random variable case. Here we are defining two random variables x and y as the proportion of time. A bank operates both a drive facility and a workup window. On a randomly selected day, let x is equal to the proportion of time that the drive facility is in use. At least one customer is being served or waiting to be served. And capital Y is equal to the proportion of time that the workup window is in use. Then the set of possible values for pair xy is the rectangle. D is equal to set of all xy such that 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1. See, here the random variables taking the values in the interval 0 to 1 only because they are the proportions, x and y are the proportion of time. So random variables can vary from 0 to 1. So the intervals 0 to 1 and 0 to 1. Suppose that the joint PDF of xy is given by f of xy is equal to 6 by 5 into x plus y square for 0 less than or equal to x less than or equal to 1, 0 less than or equal to y less than or equal to 1, equal to 0 otherwise. Here we can see that the two-dimensional function f of xy is satisfying all the conditions for a probability density function. And in this problem also we are computing the probability that 0 less than or equal to x less than or equal to 1 by 4 and 0 less than or equal to y less than or equal to 1 by 4. If you are drawing this domain, we will get a square region in the xy plane like this. See, this is the domain D where x coordinate is varying from 0 to 1 and y coordinate is varying from 0 to 1. So we are going to integrate the two-dimensional function z is equal to f of x comma y over this region. And by definition we can see that this f of xy is greater or equal to 0 because here x and y are varying from 0 to 1, and if you are adding x plus y square, that is a positive quantity, also multiplication with the 6 by 5 will give a positive quantity. So clearly this function is greater than or equal to 0. And if you are integrating over the whole xy plane, the function f of xy, we get the double integral value, integral minus infinity to infinity minus infinity to infinity f of xy dx dy is equal to here we see that the function has the domain in the rectangular, in the square region 0 to 1, 0 to 1, So x coordinate varying from 0 to 1 and y coordinate varying from 0 to 1. 6 by 5 into x plus y square dx dy. So for this double integral, see the order of integration. Here it is specified that first you have to integrate with respect to x, then with respect to y. Here the order of integration is immaterial because we have the constant limit. So we can integrate in either way, first with respect to x, then with respect to y, or first with respect to y, then with respect to x. Now we are going to integrate as in the specified order. First we are going to integrate with respect to x. So after integrating the innermost integral, we will left with integral 0 to 1 6 by 5 into integral x ds is x square by 2 plus integral y square ds is y square x within the limit 0 to 1. And evaluating this expression for the variable x varying from 0 to 1, we will get a function of y, that is 6 by 5 into half plus y square, and integrating this resultant function with respect to y. So that is an ordinary definite integral. So the variable of integration is y, and limits are y is equal to 0 to y is equal to 1. Substituting limits, and finally we will see that the total value of that integral is equal to 1. That means the volume of the surface z is equal to f of x comma y over the domain D is equal to 1, or the function fxy satisfying the two criteria. One is the non-negativity and the total double integral value, or the total volume under the surface, is equal to 1. So we can say that this is clearly a probability density function for the two-dimensional random variable xy. Now we are going to evaluating a probability for a subset defined in this domain. Here the domain is the square region with the x coordinate varying from 0 to 1 and y coordinate varying from 0 to 1. And over this square region we are marking a subset A where x coordinate is varying from 0 to 1 by 4 and y coordinate is varying from 0 to 1 by 4. This is our domain A, where this A is a subset of the previous domain D. Now for obtaining the probability, P of 0 less than or equal to is less than or equal to 1 by 4, 0 less than or equal to y less than or equal to 1 by 4, we are integrating over the subdomain, say A. That is integral 0 to 1 by 4, 0 to 1 by 4, the function 6 by 5 into x plus y square dx dy. Here we are going to integrate first with respect to x, then with respect to y. After integration with respect to x, we will get the entire thing reduced to a function of y, and then integrating the single integral, we will get the answer as 7 by 640. So this is the probability that the pair of random variables can lie within this subregion, say capital A. Next, to see the definitions of marginal probability density functions. The two marginal density functions as before, fx of x and fy of y. The marginal probability density function of x denoted by fx of x is given by fx of x equal to integral minus infinity to infinity f of x comma y dy, where this x coordinate is varying from minus infinity to plus infinity. See, here this x is fixed, so we are integrating the function by varying the y coordinate. For a given x, we have the density function given by this formula fx of x, and we can have different densities for all the possible values of x, which can vary from minus infinity to plus infinity. And similarly, we can define the marginal probability density function for y, which is denoted by fy of y and is given by fy of y is equal to integral minus infinity to infinity f of x comma y dx, and here this y coordinate can vary from minus infinity to plus infinity. That is, for a given value of y, we are integrating the density function for all possible values of x. Now from the previous example, we can also compute the marginal probability density functions fx of x, fy of y, and we can evaluate one probability that 1 by 4 less than or equal to y less than or equal to 3 by 4. So according to definition, the marginal probability density function fx of x equal to integral minus infinity to infinity f of x comma y dy. See, for the marginal density function of x, we are integrating the joint probability density function with respect to y over the whole number line. Here, because the y coordinate is varying from 0 to 1 in the given domain of f of x comma y, we are integrating from 0 to 1 only. So integral 0 to 1, the density function, joint probability density function 6 by 5 into x plus y square dy. So upon integration with respect to y, by keeping this x as constant, we have 6 by 5 into xy plus y cube by 3, 0 to 1. On evaluation we will get 6 by 5 into x plus 2 by 5, and this is true for every x which can lie between 0 and 1. But we can represent the marginal density function fx of x as a piecewise function, that is 6 by 5 into the density is 6 by 5 into x plus 2 by 5 for all values of x lying between 0 and 1, and outside this range the density is 0. So this is the standard format for representing the marginal probability density function. Similarly, we can evaluate fy of y as the integral minus infinity to infinity f of xy with dx. So here x coordinate is varying from 0 to 1 in the given domain of the joint density function f of x comma y, and substituting its value 6 by 5 into s plus y square and integrating with respect to s by keeping this y as constant, and upon integration and substitution of limits from x is equal to 0 to 1, we will get 6 by 5 into y square plus 3 by 5, and this is true for all y lying between 0 and 1. Now the standard representation of that marginal density function fy of y is equal to 6 by 5 y square plus 3 by 5 for 0 less than or equal to y less than or equal to 1 and equal to 0 otherwise. Similar to the discrete random variable case, here also we can have the independence of continuous random variables, and this concept is similar to the probability theory. If A and B are two independent events, then probability of A and B, or probability of A intersection B, is equal to P of A into P of B. Now see the definition of independence of two continuous random variables. Two continuous random variables x and y are said to be independent if for every pair of x and y values f of x comma y is equal to fx of x into fy of y. That means if you are able to factorize the joint probability density function as the product of the marginal density functions, and if this condition is not satisfied for all xy, then x and y are said to be dependent. Expected value of two-dimensional random variables. Let x and y be jointly distributed continuous random variables with the PDF of xy, then the expected value of a function of xy, that is hxy, is e of hxy is equal to integral minus infinity to infinity integral minus infinity to infinity h of xy into fxy dx dy. So these are the introductory concepts about joint probability density functions of continuous random variables. Thank you.